Hey guys, in this video we're going to look at 3.9 day 2, which covers more on inverse trig functions. Today we're going to be focusing a lot on the graphing elements of these inverse trig functions. For your warm-up, you have two inverse trig statements that you need to evaluate, which means you need to find their output values. You should pause the video, give these a try, and then come back and check your answers. When we're looking at inverse trig evaluations, we have to remember that our input is our sine ratio and the output is our angle. Our ratios have to be between -1 and +1 because those are the extrema within the graph of the sine wave. On our unit circle, we don't have any trig ratios for sine that are beyond -1 or 1. So when we look at the second statement, inverse sine of -3, this one is not possible. It does not exist because -3 is not within the domain of our inverse sine function and not within the range of the original sine wave. For the first one, inverse sine of -1/2, we can find an angle whose sine ratio is -1/2. We have to remember that we restricted the possible angles in order to make this function invertible. So for the inverse sine equation, we're only looking at angles between -π/2 and +π/2. So we are restricted to quadrants 1 and 4. Sine is negative within quadrant 4, and we have to remember that these quadrant 4 angles we define as negative angles. So sine is -1/2 at -π/6. It is true that this sine ratio also exists at 11π/6 if you were to think about that terminal ray from the positive angle of rotation, but again, that's outside of our restrictions, outside of our possible range values. So the correct answer here would be -π/6. So it's important to remember and consider these restrictions when working with your inverse trig functions. We're not looking at the whole unit circle. For each of these inverse trig functions, we only have half of the unit circle. So for sine, we're looking at quadrants 1 and 4 again. Our range is from -π/2 to +π/2, including both of those bounds. For cosine, we're looking at the top half, quadrants 1 and 2. Our angles are going to be between 0 and π, again inclusive of those bounds. And then for inverse tangent, we have quadrants 1 and 4, looking from -π/2 to +π/2, but we are not including those boundaries. Notice the parentheses on that range, and that's because at tangent and inverse tangent, we have asymptotes. So now we're going to look at the graphs of these inverse functions, starting with the inverse sine. So we have y equals the inverse sine of x. So on our x-axis, we now are going to have our ratios, that's our input, and on our y-axis, we're going to have our angles, that's our output. A quick refresh on inverse functions. We have to remember that for every point on the function f, our original function, the inverse function is going to have the inverted ordered pair, meaning that if x, y exists on our original function, we're going to flip-flop those, and y comma x is going to exist on our inverse function graph. We also have to remember that we need to restrict these domains so that they are invertible, meaning that their inverse is a function. So when I look at the sine wave, our original function f, the domain originally is from -∞ to +∞. Yesterday we talked about restricting that so that it was invertible, and our restricted domain is going to be from -π/2 to +π/2. So I'm going to highlight that portion of the graph. This is the portion that we're going to keep. Everything else we are going to get rid of when we create the inverse. The range is going to be from -1 to 1. So on this portion of the graph, I'm going to pick 3 nice points that I'm going to use to create the inverse. They are -π/2, -1, the origin 0, 0, and then π/2, 1. So when I go to create the inverse graph, I'm going to flip-flop those ordered pairs, starting with -1, negative pi over 2. 0, 0 is going to stay the same, and then we have 1, pi over 2. Okay? It's important that when we connect these points, we do not have a straight line. We keep that concavity. You can imagine that your sine wave is now going to oscillate up and down through the y-axis rather than the x-axis. Okay, there's our inverse sine wave. If you were to keep the entire sine wave, we would see that it would not be a function. It would fail the vertical line test. Again, we would oscillate around that y-axis. So that's what the entire sine wave would look like if you inverted it. Our domain for this inverse sine is going to be -1 to 1. Our range is going to be negative pi over 2 to positive pi over 2. Okay, square brackets on everything, inclusive of the bounds for both the domain and range. We'll notice, just like with our other inverse functions, the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. All right, now for cosine, we're going to follow a very similar process. We're going to take the domain of the cosine wave, which is -infinity to positive infinity, and restrict that from 0 to pi so that it's invertible, meaning the inverse is a function. The range is going to be -1 to 1. So on this cosine wave, we're keeping this first section from 0 to pi. So the ordered pairs that I'm going to use are 0, 1, pi over 2, 0, and pi -1. On the inverse graph, we get 1, 0, 0, pi over 2, and then -1, pi. Similar to the inverse sine, we're going to have a wave-like connection between these points, not a straight line. If you were to continue the rest of that inverse cosine wave to where it would not be a function anymore, you would see that it oscillates, it goes up and down along the y-axis. For the inverse cosine function, our domain is -1 to 1. Notice that that's the range of the original, and our range is going to be 0 to pi. That is the domain, the restricted domain rather, of the original function. Lastly, we have tangent getting converted into inverse tangent. The domain for the original function is all real numbers except for our repeating vertical asymptotes. So it'd be all real numbers except for pi over 2 plus pi k. That's going to get restricted so that it's invertible. We're going to keep just the first period that's centered around the origin from negative pi over 2 to positive pi over 2. Parentheses around those bounds because we do not include the vertical asymptotes as part of our domain. So we're talking about this first wave between negative pi over 2 and positive pi over 2. The range for tangent is unrestricted, -infinity to positive infinity. The points that we're going to use on this tangent wave are the origin, 0, 0, and then pi over 4, 1, and then on the other side, negative pi over 4, -1. When I look at the inverse function, our vertical asymptotes become horizontal asymptotes. So we're going to have a horizontal asymptote at y equals pi over 2 and y equals negative pi over 2. The point at the origin doesn't move. Flip-flopping 0, 0 keeps it at 0, 0. Then we're going to have a point at 1, pi over 4 and -1, negative pi over 4. And our tangent wave turns sideways so that our domain is unrestricted from -infinity to positive infinity. That's the old range. And our new range becomes negative pi over 2 to positive pi over 2. Again, parentheses because of those asymptotes. All right, now we're going to look at a few practice problems where we graph these inverse functions along with some transformations. Sometimes we may be given the equation that we need to graph, and at other times we may need to find it for ourselves. So in this first one, we are going to find the inverse function. And to do that, we're going to start by swapping our variables in the equation. And then we're going to solve for y. Once we have that equation, we're going to find the domain and range of that inverse, and then we will sketch it on the xy axes. All right, so switching x and y, we get x is equal to 2 times the sine of y plus 1. Using reverse PEMDAS to solve for y, we're going to start by subtracting 1. And then I'm going to multiply both sides by 1/2 to get rid of that coefficient of 2. The entire right-hand side and left-hand side are going to get multiplied by 1/2. So I'm going to put parentheses around x minus 1. And then to undo the sine ratio, we're going to take the inverse sine of both sides. Yeah, and so that entire left-hand side is now inside of the inverse sine function. So we have y equals inverse sine of 1/2 times x minus 1. So within this inverse sine equation, I see 2 transformations. We have a horizontal dilation by 2, so this is going to be a horizontal stretch. And then we also have a horizontal translation by positive 1. So this is going to be a movement to the right, 1 unit. Remember, those horizontal transformations are opposite of what you expect. I'm going to start by sketching out the original inverse sine wave, and then I'm going to use these transformations to change what that graph looks like. So the first one, I'm going to kind of use just like a dotted line here in yellow, knowing that this is not going to be my final graph. This is what the inverse sine wave looks like without any transformations. Next, I'm going to apply the horizontal dilation. We do this in PEMDAS order when it's factored for us. So first, the dilation, that's going to stretch this function horizontally by a factor of 2. So all of these points are going to move twice as far out from the y-axis. The one at the origin is going to stay the same. I'm going to use a dotted line again to connect those because that's not my final graph. And then the last transformation, this will be my final graph, is going to be that movement to the right by 1. So I'm going to take all of those points and move them to the right 1. And I'm going to connect these with a solid line to show that that's my final graph. The domain of this is going to be from -1 to 3, and our range is going to be from -π/2 to +π/2. On this next one, we already have the graph of the inverse sine for us, and we're going to manipulate that with transformations to create the graph of g. So I can see g of x has 2 transformations on it. I have 2 vertical transformations. We have a vertical dilation by 3, and then we also have a vertical shift or vertical translation by π/2, by -π/2. So we're going to be stretching it vertically and then shifting it down. Again, following PEMDAS order, I'm going to start with the vertical dilation. So I'm going to stretch it by 3. So this maximum is now going to be at 3π/2. And my minimum was at -π/2. It's now at -3π/2. I'm going to connect that with a dotted line because my final graph needs the shift. I'm going to take all of those points and move them down by π/2. And connect these with a solid line because that's my last transformation. It didn't ask us for the domain and range, but pretending it did, the domain would be from -1 to 1 inclusive, and the range here would be from -2 pi to positive pi inclusive of both. Now onto inverse cosine. We have the graph of inverse cosine given to us. We are going to transform it to graph the function g, which is the inverse cosine with two shifts. We have one horizontal shift and one vertical shift. This horizontal shift is by -2. So we are going to the left, and the vertical shift is by -pi/2. So we're going to be moving this one down again. Between horizontal and vertical translations, you can apply them in either order. You can do either shift first. I'm going to start with the horizontal one. So first I'm going to move all of these points to the left by 2 units. So that's 2 of these tick marks. And then next, I'm going to shift them all down by pi/2. Okay. Our domain here would be from -3 to -1, and our range, it would be from -pi/2 to positive pi/2. All right, last example is with the inverse tangent function. Here we're going to have 3 transformations. We have the inverse tangent already graphed for us, and we are going to manipulate it to create this function g. So looking at the vertical transformations, we have 2. We have a vertical dilation by 1/2, and then we have a vertical translation by -3. So we're going to have a vertical shrink and then a shift down. We're going to have to estimate where this is because remember our outputs are angles, and we don't usually talk about our angles without pi. Usually our angles are in terms of pi. So we're going to estimate where that is when we shift it down 3. For the horizontal transformations, we have 1. We have a horizontal reflection. So I'm going to do the reflection first. It's going to flip this over the y-axis, so my curve is going to flip-flop, and now it's going to be entirely decreasing. It's going to stay between those 2 horizontal asymptotes, but now you can see my slope has changed. Okay, our vertical asymptotes are going to help us find where this period is going to shift to. The vertical asymptotes are going to shrink closer to the x-axis by a factor of 1/2, and then they're going to move down 3. So if you imagine those horizontal asymptotes first moving inward towards the y-axis, so they would move from pi/2 to pi/4, and from -pi/2 to -pi/4, and then we're going to shift them down 3 units. You can also use this point of inflection at the origin to help you. Shrinking it wouldn't move it, and then moving it down 3 units, we can kind of center this period. So it's going to be close to -pi, because moving it down 3 units would put it at -3, which is just above -pi. So those horizontal asymptotes would be on either side of that. So I'm going to estimate where they are, about here and here, and then shifting that curve down so that it's decreasing the entire way. This would be a sketch of the graph of G. All right, you should take a look at the 3.9 day 2 homework. Within it, you will have some questions about the graphs of these inverse trig functions, including finding the equations, talking about domain and range, and sketching some graphs.